Okay, so for synthesis type of problems, they're going to give you a reactant molecule. So let's say we have this alcohol here, and we are converting this molecule into this product molecule here. Okay, OH is this. Okay, so synthesis type problems, they will give you the reactant molecule, they will give you the product molecule, and the question is asking you what kind of reactions you could do to transform this reactant molecule into this product molecule here. There's different strategies to go about this. What I like to start off with is find the similarities between this reactant molecule and this product molecule here. So if you guys see this 1, 2, 3, oh shoot, let's see. Three, 4, 5 carbon molecule there. That's going to be this 1, 2, 3, 4, 5 carbon molecule there, right? Because we see that this fourth carbon here has a methyl group, which is that methyl group right there, right? So our neal groups here are going to be this propyl group and this alcohol here, right? What reactions do you guys know that creates carbon-carbon bonds, neal carbon-carbon bonds? Grignard reactions, right? And we could do retrosynthesis here, and we could go backwards, right? Where if this is the new R group that we attacked, that we added in, and we see this alcohol here, right? We could say that this carbon here, which I'm going to star, is the Grignard reagent that was attached to the MGBR, right? And this carbon here, I'm going to dot, that was the electrophilic carbon, right? The carbon that was attacked. And that would make this bond here is a new bond that we form. Right? So when we go backwards here, right, retrosynthesis, let's say that this carbon here, that was the red dot, is this carbon right here. And I'm going to draw out our Grignard reagent in the first step here, which is 1, 2, 3 carbons long, 1, 2, 3 carbons long, like that, MGBR, right? Making this the starred carbon, the nucleophile carbon, because that is partial negatively charged, right? The carbon directly attached to the magnesium. Now, what do you guys think that was here at this dot carbon before that would produce this alcohol when this star attacks that dot carbon? Right, ketone, right, carbonyl, carbon double bond oxygen, because this carbonyl carbon here is the electrophile, partial positive charge that is going to get attacked by that star carbon. But when we try to make a new bond between the star and dot, that's going to break the octet rule for this dot carbon, right? Because I have 1, 2, 3, 4, 5 bonds. So to conserve the octet rule, we have to pop this double bond onto the oxygen, give it a negative charge, making it O minus, right? But the O minus here can get protonated by some acid workup, like H2O plus. Right, and I could go over the mechanism of the Grignard reaction afterwards, if you guys are not familiar with this, but this is how we can go backwards here. Um, I find the similarities between the reactant and product molecule, the differences between them, which is this new R group, that new OH group, and I know that that comes from this Grignard reaction here, using this Grignard reagent and this ketone here. Right, now, what reagent do you guys think we could use to convert this secondary alcohol into this ketone here? There's two. Yeah. Yeah. Yeah, so the OH here was in the beginning, right here, but it is not here in the intermediate, because if we try to do a Grignard reagent on this alcohol using the same reagents, let's say that MGBR, second step acid workup, this Grignard reagent here that is negatively charged, think of that as a strong base and nucleophile, right? So if it sees a base, like if it sees an acid, like this alcohol hydrogen here, it's going to do an acid-base reaction. So this Grignard reagent here is actually going to grab that hydrogen. The bond between this hydrogen being grabbed and oxygen is going to go onto the oxygen right there, giving that oxygen a negative charge. So when we get that negative charge on that oxygen right there, we're going to get this intermediate, where the second step, when we bring that in, H3O plus, is just going to protonate that O minus to become neutral OH, right? Which is going to become this OH here, which is that exact same molecule we started off with, but we want to get to this new R group on the product here. We don't want to end up here, right? And to add a new R group there with an alcohol, we have to attack some kind of carbonyl, carbon double bond oxygen. Because when this Grignard attacks this carbonyl, carbon double bond oxygen, that would add the R group on that carbon and make an O minus, which will eventually become protonated to become OH, right? Yeah. So that's why we need to have this carbonyl to add that new R group there. But what reagent do you guys know that can convert this secondary alcohol to this ketone here? PCC, right? And you could put its A product solvent as well if you want, CH2CO2. And because this is a secondary alcohol, you could have also used Jones, right? It doesn't matter for secondary alcohol, but it would matter if it was a primary alcohol. It would change, right? So this would be like a two reaction synthesis, two-step synthesis, or you could say three if you include this third acid workup step. 1, 2, 3. Right? Where the first reaction we did was oxidation. And then the second reaction we did was Grignard reaction. Grignard, right? And that converted this reactant molecule to that product molecule there. Right? Okay. Yeah. Uh-huh.
Could we also do a synthesis where we start with like a certain number of carbons, like a C5 or a C6, and we have to get the product from that? Because she said that was going to be amazing.
Yeah, like you start with a certain molecule and you want to like they give you the product and they don't give you any reactant molecule, and then you try to make a reactant molecule with a restricted carbon like C5, C4, C3. Yeah, let's do that. Any questions on this problem? Yeah. Huh?
What exactly was the purpose of the structure you do like at the bottom here?
Oh, this right here. The purpose of this route, which is the incorrect route, is to show why we needed to convert this alcohol to this ketone before doing the Grignard reaction, right? Because if we try doing the Grignard reaction before doing oxidation, it's going to do an acid-base reaction, which deprotonates the alcohol to become alkoxide ion, this O minus here, which we don't want to get there because this is our desired product here, right? So this is the incorrect route here. This leads to a different kind of product. This right here would be the correct synthesis route. Right. Okay. Let's see. Okay. And this next problem here, there's going to be different correct answers, correct routes that you guys can try out here. Yeah. Yeah, yeah. Wait, actually, I think it's best to go over that first before giving the synthesis problem, the Grignard reaction. Yeah, because the next synthesis problem that I'm going to make will involve those Grignard reactions. Yeah. Yeah. Yeah, yeah, yeah. That's good. Okay, let's go over Grignard step first. Oh my gosh. Wait, let me see if this board on the back is better. Okay. Oh my gosh, it's much better. Okay. I'm gonna rotate this around. Okay. So let me ask you this question here. What is the partial charge of this carbon right here? Partial positive, right? When we put magnesium in ether, which is the aproduct solvent, this aproduct solvent would not do anything in the mechanism. It's just there, facilitating the reaction to happen. This magnesium here is going to insert itself between that carbon and bromine, which is going to create this MgBr here. Now, this carbon here that is directly attached to the magnesium, what would be that partial charge? Partial negative, right? So we changed the polarity of this carbon here. Before it was partial positive, electrophilic. And once we put the Mg there, creating this RMgBr, the carbon directly attached to the magnesium is partial negative charge, making that the nucleophile, right? And we could use this nucleophile to attack three different kind of things. We could attack haloalkanes, carbonyls, or epoxides, right? So let's talk about attacking haloalkanes. Right. So if I have this Grignard reagent here, MgBr, and I were to react it with this haloalkane here, what I'm gonna do is I'm gonna use the star and dot technique where I like to star my nucleophile, which is this partial negative charged carbon right here. And I like to dot my electrophile, which is this partial positive carbon right there. What reaction do you guys think is gonna happen between this nucleophile and the electrophile with a good leaving group here? It's one of the reactions you guys learned, but you guys haven't seen this specific reagent for this reaction yet. It's one of the SN2, SN1, E1, E2 reactions. SN2, right, where this is the substrate, the primary substrate that is that has a good leaving group. So this nucleophile here is going to attack that substrate there, kick out that good leaving group right there. Right. When this happens, this MgBr just dissolves away in the solution. Right. It goes away. It disappears. So this is where a lot of people get tripped up on, is when you are trying to connect this nucleophile and electrophile, right? Because sometimes people add too many carbons, sometimes people like add too little carbons. So that's why I star and dot it, because if you draw out the starred molecule, which is going to be this molecule here, that is now bonded to this dot carbon right here, right? Making this the neo bond between the star and dot carbon, right? This bond here, the neo bond, came from this attack, right? And now this dot carbon here is attached to this methyl group right here, which is that methyl group right there. The Br is no longer there because we kicked that Br out as a good leaving group. And you can say that that is Br minus now as a side product, right? But this is the alkane that we get right here from this reaction. We added carbon-carbon bonds, right? Now, the other reagent you could react this Grignard with is with a carbonyl, specifically an aldehyde, or a ketone. Right. Let's say we use the same Grignard reagent, MgBr here, and on the reagents, we have first step, this ketone, second step, this acid workup. What, so let's say this is the partial negative charge. Which atom here is going to be our electrophile? Which atom is going to be partial positive charge? Yeah, the carbon-neocarbon. The carbon with the double bond is our electrophile. So this nucleophile here, when it goes to attack that carbon-neocarbon right there, we're going to break the octet rule, right, for this carbon, because we're trying to make a new bond between this dark carbon and that dark carbon. That's going to be 1, 2, 3, 4, 5 bonds. That's not good. We don't want that. So to conserve the octet rule, we have to pop one of these bonds of the double bond onto the oxygen right there. But what charge would this oxygen get as a result, as it gains a pair of electrons? Negative charge, right? So when we draw out the intermediate of this, we're going to have, so I'm going to draw out this molecule like that. And I'm going to say that this is the O minus, this is the new bond that I just formed, right? Where this is the dot carbon, this is the starred carbon. making this the new bond between the star and dot carbon right there, right? This new bond here came from that attack right there. Okay. Now we see that this star carbon here is attached to 1, 2, 3 other carbons, which is going to be this 1, 2, 3 carbons like that, right? Now, what do you guys think the second step is going to do? The H3O plus is going to do to this O minus protonate, right? To make it neutral, right? This O minus here is going to grab one of the hydrogens of the H3O plus, and the bond between that hydrogen and oxygen is going to kick off onto that oxygen, kicking off a water molecule, making this O minus into a neutral OH. OH, boom, 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 like that, right? Where you notice here that this ketone here was that ketone, but instead of the carbonyl, it is now an OH, and then this is the new R group we added. This new R group that we added came from that Grignard reagent there, right? Okay. Yeah. Yeah. Any questions on this mechanism? Okay. So instead of a ketone, you could have seen this with an aldehyde as well. So instead of this methyl group here, if this was a hydrogen, right, then this would have been a hydrogen right here, right? If that was a hydrogen, this would have been a hydrogen as well. Same mechanism, just different groups attached to the dot carbon. Okay. Now, epoxides. Let's see. I don't know if when Wei goes over the epoxide, does she give the epoxide in wedges and dashes usually like this, or does she give epoxides in flat bonds like that usually? Oh, this one, the second one. Okay. Let's do that. Right, because that is gonna have to like we're gonna have to invert the stereochemistry here, right? Okay. So let's say that this carbon here is substituted with isopropyl, ethyl, and let's say this is a methyl group right there, right? If I react this with the Grignard reagent that we had earlier, this RMGBr, the second step, acid workup, this carbon here directly attached to magnesium is still partial negative charge because it is still a Grignard reagent. But this epoxide here, this 3-membered ring is unstable because it has a lot of ring strain, right? So these carbons here are reactive. When we open up epoxides, if we're in acidic conditions, do we open up the epoxide at the more sub position or the less sub position in acidic conditions? More sub position, right? So in basic conditions, we're gonna attack the epoxide in the less sub side of the epoxide, right? Whenever you see negative charges, then think of that as basic conditions. So let me write that down here. So acidic conditions is going to be like when you see an alcohol with a strong acid like H2SO4. Basic conditions is when you see a negative charge solution like RONA or ROK, or even Grignard reagents, RMGBr, right? Because we have negative charges on these oxygens here, and that are right there attached to the Mg, right? Because whenever you guys see a sodium or potassium, always associate that with a positive charge. That means that whatever is attached to this positive charge spectator ion is negatively charged. And negative charge solutions are basic conditions, right? Because they want to grab a hydrogen. They want to attack a hydrogen. So would you guys say this is in acidic conditions or basic conditions? Basic conditions, right? And don't look at this second step acid workup, right? Because that is not included in the reaction yet. If you see step-by-step reactions like this, 1, 2, and 3, always look at the first reaction first and react that with the reactant, and then use that product of the first reaction to react with the second reactant, right? So if we're in basic conditions here, would we attack the more or less subside of the epoxide? Less subside, right? Because in basic conditions, think of it like an SN2 like reaction. In SN2 like reactions, do we prefer to attack the more or less subside, and why? And why do we prefer to attack that side?
Less steric hindrance.
Yep, less because less steric hindrance. We want the nucleophile to attack the less subside because there's less groups attached to it. More space for the nucleophile to come in and attack, right? So this carbon here is going to be attacked by this Grignard reagent, and we're going to kick up the epoxide this direction. The reason why we have to kick it off is because that's going to break the octet rule of this carbon right here. This carbon already has 1, 2, 3, 4 bonds to the invisible hydrogen. We're trying to make a new bond between this carbon and that carbon right there, breaking the octet rule. So we have to kick off that leaving group, that side, right? And this is going to also do a backside attack for SN2. And what happens to the stereochemistry of backside attack? Does it invert stereochemistry, maintain the same stereochemistry, or randomize, racemize the stereochemistry? Invert stereochemistry, right? But because this epoxide here is not a wedge or a dash, it's not easy to invert, right? Because if this was a wedge epoxide, we just easily invert that to a dash epoxide. So the way that I'm going to invert it here is that I'm going to see, can you give me the purple marker? Yeah, thank you. Right. This base of the epoxide right here is going to be our line of reference, right? And if that's our line of reference, we see that these two bonds are on top of the line, right? So when we're inverting this bond right here, this bond has 2 electrons. Those 2 electrons are going to go onto this oxygen, giving it a negative charge. The new bond here is going to be the inverted bond of that, which is going to go down like this, right? Where if this was my dot carbon right here, which is this dot carbon, this is my starred carbon right here, making this the new bond between them. And this would be my line of reference right here, right? Because before this bond was up on top of this line. But when we invert the stereochemistry of this up bond, it's now going down right here, right? Down in reference to that line. This starred carbon right here is attached to 1, 2, 3, a propyl group, which is this 1, 2, 3 propyl group right there, right? Now, everything else is gonna stay the same. The dash was up here, so let's keep that dash up there, wedge down there, so keep that wedge down there. Methyl, it was up here, so just keep that wedge up there, right? Now the acid workup here is just gonna protonate the O minus to become OH plus, neutral OH.
So the stereochemistry stays the same?
Stereochemistry stays the same on the left side, right? Because this left side carbon here is untouched. Yeah, nothing attacked that carbon, so it's gonna stay the same. But because this carbon here got attacked by this carbon, we're inverting the stereochemistry of this right carbon right here, right? Mm-hmm. And that would lead to our neutral OH product molecule here. Right. Like that. And I know on the problem set that this was not shown as one of the answer choices, right? Because this came from a Leibniz problem set. You would have to rotate this single bond right here to get to the right answer. And that's going to require like more steps. Do you guys want to go over that process too, or is this good for Grignard reaction? Yeah. Yeah. Go back, explain a different back.
No, move the board back.
Oh, move the board back. Yeah. Sorry. Let me move the board back. Yeah. Is this good or okay? Yeah. Yes.
So if we were in acidic conditions,
Mhm.
would it attack the more substituted carbon?
Yes. If we were in acidic conditions, it would attack the more substituted carbon. And I could go over that after I go over synthesis bonds with the Grignard reagent with the restriction, and then we could go over epoxide opening more clearly in more details with this like rotation of bonds thing for Weiss class. Right. Yeah. Okay. Mhm. Yeah. You want water? Mhm. Thank you.
stereochemistry when you attack it from the red side?
Right.
Because you see the CH3, which is wedged, right?
Yeah.
It's still wedged in the second one. Why is that?
Right. Right. The stereochemistry that we're inverting is going to be the bond that we break.
Right.
This bond here is not being broken off, so that bond stays as a wedge, right? So because we're breaking this bond here, we're inverting this flat bond. So we can't invert it from a wedge to a dash or dash to a wedge, but we do have to invert this bond that is going up on top of this line, the purple line right here, the base of the epoxide, to go down. So this is the bond that got inverted right here. Inverted bond. Inverted.
What's the bonds connected to the oxygen in the first one?
This oxygen here,
Yeah, that's from the other one.
yeah, this bond here is up and it stays up because nothing attacked that bond, so we don't invert that bond right there. And this oxygen is now negatively charged because it gained 2 electrons from that bond right there, which is why it's now negatively charged. But when this carbon here goes in to attack this carbon, it attacks on the back side, right? It goes on the bottom. That's why the bond is on the bottom now, right? Because it's inverting the bond that it kicks out.
And I see that you labeled it with the red. See, that's where the bond came from.
Oh, this right here, or
The red star.
red star. Oh yes, this red star here is this red star carbon right there.
I'm just confused where that extra bond came from.
Oh, this extra bond right here? Yeah, so this extra bond came here, like those 2 electrons came from the 2 electrons from that
Oh,
carbon right there. Like think of it as a pair of electrons on that carbon with the green agent, right? Uh-huh. Yeah, that's good. Good questions. Yeah. Uh-huh. Yeah. Yeah, if the original epoxide was a wedge, like let's say we have this wedge epoxide here, and we have these groups attached to it, and we use the Grignard reagent like this, MGBR, first step, second step, acid workup. This is our nucleophile, the star, and because we're in basic conditions, we want to attack the less subposition, this carbon here. And because we're breaking this bond right here, we're going to invert that bond. So when we invert it, everything here stays the same. Wedge, O minus, this stays there. But instead of a wedge bond, we now have a dash bond to this star carbon, which is attached to a 1, 2, 3 propyl group, 1, 2, 3 propyl group like that. Right? And then we just protonate the O minus to become OH to get the final product. Right? So it's easier to invert wedge to dash or dash to wedge because we know what the inversion is. It's harder to invert the flat bonds, right? Because we're inverting the flat bond relative to this base of the epoxide right here, the base of the epoxide like that, right? And some questions might be tricky because you might see some epoxides like this. Right, where now the base of the epoxide, the line of reference, is going to be this line right here. So when you attack this carbon, you have to like reference this line at this angle right here, right? But the way that I drew it here is like straight horizontal, like that. Yeah.
So in the example you drew, why didn't the wedge become a dash when you were changing the stereochemistry?
Oh, why didn't this wedge become a dash?
Yeah.
Yes, because when we attack this carbon right here, look at the bond being kicked off, which is this bond right here, right? And that bond is the bond we're inverting. So when we invert this bond, we have to invert it in reference to this line, which is this down bond right here. This bond here does not get kicked off at all. Like we don't touch that bond, so that bond stays untouched, and we maintain that bond. So think of that as a decoration. Like it's not going to do the reaction, right? It's not going to interfere with the reaction, right? But in this problem right here, right, we are kicking off that wedge bond right here. This wedge bond is getting kicked off, which is why we invert that to a dash right there, right? But this one here is not getting kicked off. Like it's not getting kicked off at all, right? Yeah. Uh-huh. Yeah. For the epoxide reaction, yes. Uh-huh. Yeah. So do you get why this carbon here is negatively charged, the one that is directly attached to the magnesium? Yeah. If it's negatively charged, that would make it the nucleophile. right? And in organic chemistry, nucleophiles will always attack electrophiles, not the other way around, right? So the negative charges will go towards the positive charges, right? So in the first reaction here, we have a negative charge carbon attacking this positive charge carbon right here, right? But we have to kick out this good leaving group to conserve the octet rule, right? So when we do that, we make this new bond between the star and dot. This is the star carbon, this is the dot carbon. And we said this dot carbon is attached to this methyl group right here, right? So SN2 reaction. Yeah. For the carbonyl aldehyde or ketone one, this is still our same nucleophile, the star, but our electrophile is now attached to a carbonyl, carbon double bond oxygen. When we attack that, we have to pop this double bond onto the oxygen, giving it an O minus charge. And this O minus charge here is just going to get protonated with the acid workup to become neutral OH. Right? It gains a hydrogen and a +1 charge to become neutral. Right? For the epoxide one, this is the hardest one in my opinion. You have to know that this Grignard reagent, because it is negatively charged, we are in basic conditions. And when we open up epoxides in basic conditions, we attack the less subcarbon. So that's the regiochemistry of it, right? More or less subside. The less subside is going to be attacked in basic conditions. But the stereochemistry is going to be the same for both conditions. We invert the stereochemistry, right? So when we attack this less subcarbon right here, we have to kick up this bond onto that oxygen right there, right? And the bond that we kick up open is the bond that's getting inverted. So this is a flat bond right here. So to invert a flat bond, we have to invert it in reference to like this base of the epoxide right here, which is the line in purple, right? This bond right here is going up right now. So we have to invert it going down in reference to that line, right? Everything else stays the same. Stays the same dash, wedge. This bond here that is up, it stays up because nothing touched that carbon. And that's why it's now an O minus right there because it gained a pair of electrons from this bond right here being broken onto that oxygen. This wedge bond here does not get inverted because we don't kick that bond out, right? It stays untouched. That's why it's a wedge. Does that make sense on why? Yeah, somewhat. Which part is confusing for you? Uh-huh. What about this one here? Like the epoxide with the wedges. If we attack this less subside and we kick up this wedge, we invert this wedge to a dash. Right? Does that make sense? Like the wedge to a dash. This is harder to invert because it's not a wedge or dash. Like it's a flat bond. So that's why we have to look at this bond right here, the base of the epoxide, right? And this bond here is going on top of the line. When we invert that bond, it has to go on the bottom now. It's on at the bottom side of the line, right? So we can't invert this to a wedge or dash because it started off as a flat bond, if that makes sense. Yeah. Yeah. No problem. Okay. Okay. Now we could do synthesis with the restricted carbons like C4, C5, C3 right here with the Grignard reactions, right? Mm-hmm. Okay. Oh no. Oh, I am. Oh no. Oh shoot. Oh my god, I didn't know that. Oh my god. Wait, hold on. Hopefully this works. Oh my god. Oops. That was an accident. Okay. I am. What the heck? Okay. Yeah. Oh my god. I was like, why is this marker so hard to erase? Oh my gosh. Yeah, I know. Oops. Okay, I need to use different markers. Yes, please. Do you guys have markers too, like dry erase markers? Yeah, thank you.
I mean, this one seems good.
Yeah, that one, the purple one? Yeah. I'll probably use that. um, a cloth eraser. There should be around here. Let's see. Oh, hey, sorry. Yeah. Oh.
Okay, let's do it.
Okay, let's do
Start
it. Yes, here. You could use this as well.
Okay. I don't know if this right here is gonna work.
Yeah. Oh my god.
Stay in practice like other.
I hope everyone in the video enjoys me in my pajamas. I was not getting dressed.
Yeah. It's finals season.
My parents dropped me off with the biggest coffee they could get at Phil's, and I appreciate them for it.
That's good.
Like, we're gonna get you coffee and then leave. And I'm like,
And then winter break after finals, 3 weeks off. So good.
I'm so done with this place.
Yeah.
I just want to keep my hay. I'm working so hard.
Yeah. And Grignard reagents, right? I feel like that's gonna be included in one of the synthesis problems. Like that's a big reaction. Grignard reaction. Yeah. Thank you. Yeah.
So what exactly makes something a Grignard?
When you see MgX, where X is any halogen like chlorine, bromine, iodine, that's a Grignard reagent, right? That's a part of an organometallic, which is a negatively charged carbon, you could say, right? Because the carbon directly attached to the magnesium is the nucleophile, the negative charge. Grignard reagent is a type of organometallic. The other type is going to be organolithium when you see RLI, lithium, right? And the carbon directly attached to the lithium is also going to be negatively charged, right? So that carbon there is going to be the nucleophile, which is going to do the reactions that I just went over here. You can attack a haloalkane, epoxide, or carbonyl, right?
For the halogen, put that next. I know what halogens put.
You get to choose. Yeah, like for reactions, I would go with bromine because that's the most common one. Yeah, because you could see chlorine as the reagent or iodine as well, but bromine is the most common one. Yeah. Mm-hmm. Yeah. Thank you. Thank you for that.
Thank you. Put on the table, actually.
Yeah. Uh-huh. Yeah, Li is like MGBR. Think of it as MGBR. Li. Yeah. Okay. Thank you. Okay. Besides a little bit. What? Okay. Now, if they give you something like this, and this is the product of the problem. They might ask you to synthesize this molecule with no more than 5 carbons, right? Let's say synthesize this molecule. The restriction, C5. Restriction, C5. Meaning that your reactant molecule cannot be bigger than 5 carbons. Right. So find your disconnections and try this for a few minutes, and we'll go over this. Right. Yeah. Uh-huh.
Is there ever a time for Grignard where RLI is better than
There are like some cases, but you don't have to worry about that for 118.
So it's fine if we use either, or would you say it's better to just use MGBR?
You could use either in this case, yeah. So if you use Li, then it would be the same as MGBR. Yeah. No problem. Yeah.
Would you say synthesis if they give you the reaction product and you try to find like the intermediate?
Yeah. So usually in synthesis problems, they give you the reactant molecule and the product molecule, and you try to transform that reactant molecule to the product molecule. But this one here is a little bit harder because that's the product molecule that you're trying to get to. So this is not going to be the reactant
So
right
you
here.
have to find the reactant?
Yeah, you have to make up your own reactant and reagents to get to that product. But the reactant you make cannot be longer than 5 carbons, right? Yeah, it can be shorter or equal to 5 carbons, but not longer than 5 carbons. So we could put this. Yeah. Yeah. How are you guys feeling about the HNMR spectroscopy IR, like predicting unknown product molecule? That's fine. My practice, yeah. The synthesis one?
Yeah, it's this
And alcohols.
Yes.
Yeah. I see, I see. Yeah. It's gonna happen, yeah.
Oh yeah.
Yeah, put this back. Excuse me. Yeah. Mm. Mhm.
Yeah.
Yeah.
Dude, I started all the way from an
Uh-huh.
alkane. You see,
Extra practice.
extra practice, and it was like, I don't know how far back he goes.
Am I amazing as someone
Mhm.
Or
Yeah.
if it works, it works. I know what I'm doing, but like, exactly.
See, any questions here? Any questions here? No, okay, that's good. Yeah, yeah.
This is retrosynthesis.
This is retrosynthesis. Yes, going
Are you
backwards.
supposed to learn that?
Uh,
18A?
118A. Some professors, yes. Like for way, probably. For way, yeah, for
He
way.
said it's definitely gonna be on the exam.
Like something like this. Yeah.
This retrosynthesis.
Leavens just gives us
Mhm.
reactive product.
Yeah, leavens. You don't have to do this for leavens. Yeah. For Fahrenheit, I don't think so. Yeah. But it's good for practice anyway, just to understand it. Nusuri for sure. Nusuri, she went over these problems a lot. Yeah, this was, yeah. Mhm. Yeah.
So this is like related to
Uh-huh.
the first example you gave.
Yes.
So how do you know if a haloalkane can form a Grignard reagent? So like
Mm.
if you're given multiple, because like I've been stuck on this problem for a very long time, and
Right.
yeah,
Right. So selected alkanes can form a feasible Grignard reagent.
yes,
Magnesium.
there are only two answers.
Those are the two answers, right?
Yeah.
So when you form a Grignard reagent, right, like MgX,
Mhm.
the carbon directly attached to the magnesium is going to be negatively charged,
Yes.
which is going to be a strong base and strong nucleophile.
Yes.
So when we form, let's say, a Grignard reagent here with MgCl, that MgCl is going to react with the alcohol. Like that is a part of, because this alcohol here has an acidic hydrogen.
Yes.
So it's going to do a intramolecular acid-base reaction. So that's not feasible.
Oh,
Right.
okay.
If we put MgCl here, that's going to attack this carbonyl intramolecularly. Right. So we don't want that because
I
it's
see.
going to attack itself, basically. When we use this one, there's no other group that can be attacked. Right. There's no carbonyl, there's no alcohol. So this is good. If we use this one, this alkyne hydrogen here can be deprotonated. So that's not good. But this one here is good because that's an ether, which is unreactive. Right. So it should be these two here.
Yeah, I
Yeah.
don't know how you would be expected to know that without knowing that.
If it reacts with the
Yeah.
thing. Is this Farhat or
This is Farhat.
Farhat? Yeah, yeah. Dang. Dang.
Thank you.
Yeah, no worries. Uh-huh. Yeah. Let me see what you have so far.
I know you have to this, right? So
Mhm.
that's
That's
I
correct.
forgot what goes to make that a ketone.
Yeah. So where could the ketone come from? But actually, I'll explain it later here. Explain it later here. Yeah.
So
Yeah.
I'm trying to go backwards.
Uh-huh.
So
Right. So when you try to go backwards, where do you think this alcohol could have came from? What functional group? Carbonyl. Right. So let's say that this carbon here is the carbon that is holding the carbonyl. Oh, this is terrible. Let me go back to the purple one. Right. So if we go backwards here, we can say that that carbon that I just dotted is this carbon here that has the carbonyl like that, right? And let's say that that was the dot, and let's say this is the star right here, the Grignard reagent. So we're gonna make a disconnection between this star and this dot right here, because that's the new bond that got formed between them. What can we add to make this starred carbon negatively charged? Right, let's say Grignard reagent, right? First step, we could say that this is a star, the same exact molecule as the star right here, but to make this carbon negatively charged, we attach an MgBr to it to make it negatively charged, which is going to attack this dot carbon, pop the bond onto the oxygen, which gives it O minus charge. And what can we add as a second step to make that O minus charge into neutral OH? H3O plus, yes. Okay, now let's go backwards even more. You could say that this is your reactant here, and that's it, because that's 5 carbons. But let's say that to make it more practice, let's say it gives me cyclopentane like this, just for practice, right? And let's try to add that carbonyl there. If this is a cycloalkane right here, there's only one reaction that you could do with this, and it's the very first reaction you guys learned, halogenation, right? So let's do Br2 H-nu to add a bromine on that carbon right there, right? Now, let's say that this carbonyl came from one of the alcohol reactions you guys learned. Oxidation or reduction? Oxidation, right? And what reagents could we use to oxidize this alcohol to that ketone? PCC, right? CH2, Cl2. Now, we are going to try to convert this bromine into this alcohol. This is going to be a confusing one, but do you guys know how we could do that? Like, this is a little bit tricky, Ester hydrolysis, yeah. So SN2 looks like the route, right? But when we try to do NaOH, right? But it's going to be ester hydrolysis. When we do NaOH and water, this is a secondary substrate. This is our good leaving group. This OH minus is a strong base. So if you look at the table of the reactions, strong base, secondary substrate, good leaving group, E2 reaction. So it's going to create this alkene right here, right? Where it's this OH here is going to grab that hydrogen, make a double bond there, kick out that leaving group. So it looks like we want to use this OH minus to attack that carbon and kick out the bromine to get that OH there, but we can't do OH minus right there. We have to do a different route, ester hydrolysis, right? Which is going to be CH3, COO, Na, DMSO. And this CH3, COO, Na looks like this. Whenever you see an Na, what charge is that associated with? Positive charge. Whatever is attached to it is negative charge, which is this O minus right here. So this is the CH3, COO minus. And this CH3, COO minus here is a weak base, strong nucleophile. It's a strong nucleophile because we have a full negative charge on that molecule right there. But what do you guys notice that this negative charge can do with the carbonyl that makes it more stable? Resonance, yes. And because it can do resonance with the carbonyl, does that make it more or less stable? More stable. And if it's more stable, is it more or less reactive? Less reactive. That's why it's a weak base. So it's not going to do E2 because E2 works with strong bases. It's going to do SN2. So this minus here charge is going to attack this carbon, kick out the leaving group to give us this ester here. Right. Where this oxygen here is that oxygen that attacked that carbon, making this the new bond. Right. And this carbonyl group is that carbonyl group attached to that oxygen that attacked this carbon. And this is what we call an ester functional group. A carbonyl, carbon double bond oxygen, next to an OR group, ester. And we could hydrolyze this ester using NaOH, water, second step H3O plus, or just H3O plus and water, right? So this reaction here, ester hydrolysis, you do need to know the reaction, right? But the mechanism is 118C, the beginning of 118C. I know, so I don't know why they showed you guys this, ester hydrolysis, because that's a 118C reaction. But you do need to recognize that when you have an ester, you can convert it to an alcohol by cutting that bond using one of these reagents here, right? Water and base or acid.
Okay, so
Yeah.
So it goes from Br to OH with ester hydrolysis.
Yes. Br to
That one is OH.
oh no, so it first goes to Br to this ester
From that.
to form the alcohol, right? Because we can't make this alcohol from a Br directly. Like when we try to make it directly with the OH minus,
So it's a two-step process.
yeah, 2-step process to convert this Br to OH.
So it turns into that,
Yeah, it turns into this ester.
And then we don't know that mechanism. That's when it's
Yeah, you-
but we know that it turns into that.
yes, we know that this turns this into that. Yeah, you need to know that. Yeah.
So wouldn't it be 3 steps because the
Mhm.
BR and then the ester
2,
and then
3,
the PCC
4, 5.
5.
Yeah, 5 step synthesis.
Okay.
Right. The three. Yeah, it will be 5 steps overall because this first reaction here was bromination. Second reaction we did was, so this is not the correct route because I created this alkene. We don't want that. SN2 to create this ester, and then this one here is ester hydrolysis, and then we did oxidation, and then we did Grignard.
Wait, you said SN2?
Yeah, SN2 with this carboxylate and this haloalkane here. Right.
And
This,
the CH3COO.
yeah, CH3COONA attacks that carbon, kicks out the leaving group to substitute the bromine with that group to create the ester there.
That makes sense.
Yeah. Yeah.
For hydrolysis,
Yeah.
do we need the second step H2O plus? Because isn't H2O like a polar protic solvent?
It is a full product solvent, but in what you can see,
Yeah, you just
you're gonna learn that when you just use a base right here, that base can deprotonate the carboxylic acid. Well, actually, in this case, you could just leave this step out because we don't care about the carboxylic acid. Because after this step, our side product is this carboxylic acid here, right? Which is what you're gonna learn in what you can see. So you can basically just do hydrolysis with the base and water, yeah. But on the problem set, I think she put the acid workup as the second step as well for Way's problem set. Yeah. Yeah.
And then for
Yeah.
ester hydrolysis, you have to write the NaOH H2O H3O plus. The steps, the 1 and 2.
1 and 2, yeah. Yeah, NaOH, H2O first step, second step, H3O plus.
Okay.
Yeah, yeah. To get the final product. Mhm. Right. Yeah. Jones. Yes, you can also use Jones because secondary alcohol to ketone could be oxidized by using PCC or Jones. Doesn't matter. But for primary alcohol, it would change. If you use PCC, it turns into an aldehyde. If you use Jones, it would turn into a carboxylic acid if you use a primary alcohol, right? So you could use PCC or Jones. Yeah. Yeah. Okay. Yeah.
In the notes, she
Uh-huh.
used H2O OH minus HMPA to
Uh-huh.
convert this to this,
Oh, HMPA,
and then from here
Uh-huh.
you do PCC to ketone,
Ketone.
and then I use Grignard
Grignard.
to do here. Would that be correct too, or
Yeah, if she put that BR directly to that secondary alcohol with H2O OH HMPA,
Mhm.
does that, then that would work as well.
okay?
Yeah, so let me put that down. Yeah, thank you
Okay.
for showing me that. Yeah. So is that for waste class or Fahrenheit? Waste class, yeah. In waste class, there is a reaction that can convert the haloalkane to the alcohol directly in one step. Right. Which is going to be H2O, OH minus, like NaOH or KOH, and HMPA. So that 4-letter solvent, H2O hydroxide, would convert this bromine into the alcohol. And I would guess that this HMPA here weakens the basicity of the OH minus, which prevents the E2 reaction happening here. Right? And because the HMPA weakens the basicity of that OH minus, it's going to do SN2 instead.
So
Right.
you can actually do that.
Um,
Just use that one step.
yeah, with this solvent right here, because the solvent like affects the reaction a lot. This solvent here can weaken it, converting this bromine to the alcohol in one step directly. Right. Uh-huh. But I did not learn about like this. I learned it in the ester hydrolysis route. Right. Hydrolysis.
Has Wade even taught about ester hydrolysis?
I'm not sure. I'm not familiar with her class. It was on the homework for Levin's problem set or like Wade's problem set. Mm-hmm. Yeah. Let's see. How are ether reactions for you guys? Like Williamson ether synthesis and reacting it with acid and water? Ether, yeah, yeah. Let's go over that. And I have to look at Wei's and Farhad's notes as well because there's one reaction that will be different depending on the professor, like the list of what carbon to attack. Right.
I have a quick question.
Yeah,
When you do the Grignard reaction,
yeah.
can you do a 3-step Grignard where you synthesize your own Grignard, or can you just put
Uh-huh.
CH3, CH2, MgX, or should you put
As a separate step, you could put it as the RMGX, like
RMgX?
as a reagent. Yeah,
Okay.
right. You could do that.
Reagent?
Yeah, yeah. But if you start off with a halo alkane, and you want to make that halo alkane into a Grignard reagent, then you'll put the Mg there to create the Grignard reagent, and then as the reagent, you could put the carbonyl there or halo alkane there to react it with. Yeah, yeah. Ether?
An ether with ether, you react with H2SO4 and it brings the ether into like two alcohols.
Uh-huh.
I just
Yeah.
not really sure how that works.
Right. I was gonna go over there right now. Yeah, yeah, yeah. That's good. Let's see. Yeah. Okay. So, an ether functional group is ROR. ROR, right? An oxygen that is in between two hydrocarbon chains. So examples would be like that, like this, and this ether here is a cyclic ether, right? Because this oxygen here is still in between two R groups, carbon, oxygen, R, and there's a specific name for this cyclic ether, which is epoxide, right? Now, one reaction that can create ether is Williamson ether synthesis. Wes. Right. And there's two reactions that go with this. The first reaction is going to be acid-base reaction, you could say. Acid-base. Right. Deprotonate the alcohol. The second reaction is going to be SN2. Right. So this is a two-step synthesis, Williamson ether synthesis. If I start with this alcohol here, and I give you these two steps, first step NaH, second step this halo alkane right here. Whenever you see Na, sodium, positive charge. Whatever is attached to it is negatively charged, H minus. This H minus charge here, the hydride ion, is one of the strongest bases we have, right? Because the negative charge is on a very small atom, hydrogen, and it's on a non-electronegative atom. So this is very unstable. And because it's very unstable, it's very angry, very reactive, making it a super strong base. So this super strong base here is going to grab that hydrogen of the alcohol, and that bond between the hydrogen and oxygen is going to pop onto that oxygen right there as 2 electrons, right? Which is going to give us this negative charge on the oxygen and H2 as a side product, right? Coming from this hydrogen, grabbing that hydrogen right there. Now this O minus here, because it is negatively charged, that is going to be our nucleophile. That's the end of the first step. Now let's bring in the second step, the halo alkane here. What do you guys think is going to happen between this nucleophile and this electrophile with the good leaving group? SN2, O minus attacks that carbon, kick out the bromine to give us this ether here, right? Where this is the new bond that we formed between the oxygen and carbon that got attacked, which is attached to this methyl group, and Br minus got kicked out as a side product, creating us this ether, right? So Williamson ether synthesis, Wes, is a two-step synthesis problem. The first step was acid-base, where we deprotonated the alcohol to create this nucleophile alkoxide ion. Then the alkoxide ion nucleophile is used to do SN2 to attack that electrophile as SN2 to create this ether right here. Yeah.
Is this a reaction where it's like dependent on like if it's a tertiary or secondary carbon, it's SN1 or SN2, is it always SN2?
Oh right, because like if this was like primary, secondary, it would work best with primary and secondary. Tertiary is gonna be a little more iffy because it's too much steric hindrance. Right. So if it's tertiary, then I would say no reaction. But I haven't seen too much examples of that. I've only seen examples with primary or secondary substrates doing SN2. Right. But if it was tertiary, I would say no reaction. Yeah.
What was SN2?
Um,
Tertiary?
yeah, if this carbon here was tertiary, I would say no reaction because this SN2 reaction would have no space to attack that carbon. Too much steric hindrance, right? Too bulky. It works best with primary or secondary substrates for SN2, right? Right. Let's get, yeah. So this was an intermolecular Williamson ether synthesis. We can have an intramolecular one, right? Where the nucleophile and electrophile could be on the same molecule, which attacks itself, forming a ring. So before I go over this reaction with you guys, let me show you guys this type of reaction. Intramolecular reaction, which is going to show up again in 118B and C, right? And this reaction is going to happen when the nucleophile is on the same molecule as the electrophile, right? So the nucleophile is going to attack itself, and this will always form a ring. Always forms a ring, aka a cyclic molecule. Molecule. Right. Okay, so let's do this. Let's. Okay, and the only reagent that you're going to see here is NaH. Right, and let's see, what would the NaH do to this molecule here? What do you think the NaH is going to do here? Right. H minus is going to deprotonate that alcohol hydrogen, giving that oxygen a negative charge, which is the nucleophile. Now, we don't have any second step of electrophile, right, as a separate molecule, but we do have an electrophile present somewhere in the molecule here, which is going to be that carbon right there. That's partial positive charge. So that is our electrophile. This O minus here is our nucleophile. This nucleophile is on the same molecule, like this overall molecule, as the electrophile, making this an intramolecular reaction. So when this O minus here comes around to attack that carbon right there and kick out the leaving group, we're going to make a ring, right? And the ring that we're going to make is a 1, 2, 3, 4, 1, 2, 3, 4, 5 membered ring, right? I always start my number 1 atom on the nucleophile, the atom that is attacking. And I always end my numbering system at the atom being attacked, the electrophile, to know how many membered ring we're forming here. It attacks here because this carbon here is partial positive charge, since it's attached to this electronegative bromine atom. And this bromine atom here is a good leaving group. Good leaving group, right? So it's still SN2, but it's on the same molecule as the nucleophile, right? Making it an intramolecular reaction, right? And so to predict the product here, which is a little bit confusing, but since you know you're making a 5-membered ring where one of your atoms in the 5-membered ring is an oxygen, draw that template out like that, right? This is the template of the molecule, the product molecule. Then once you have that template down, you would number it as you did 1, 2, 3, 4, 5, where your number 1 atom was the nucleophile atom, the oxygen right there, right? Then you just draw whatever is attached to the numbered carbons, the decorations. Carbon 2 is attached to an ethyl group, which is this ethyl group here, 1, 2. Carbon 4 is also attached to an ethyl group there. Carbon 5 is attached to a methyl group right there. It was attached to the bromine, but we kicked that bromine off as the leaving group. And this would be our final cyclic ether product here, a ring. Yeah. And then you're gonna see this with epoxides as well, which I'm gonna show right here, right? Because let's say we have this, 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 that, bromine, and I react this with NaH, right? So this NaH right here is still going to deprotonate the alcohol, giving us an O- charge, alkoxide ion. Right. But our electrophile is now on this carbon. So when we attack this carbon here and kick out that leaving group, we're going to invert this dash into a wedge. This is going to do the backside attack, inverting stereochemistry, right? So that's going to give us this product here. And what is this functional group you guys see right here? Epoxide. So this is how we could form epoxides. And I think this showed up on one of the synthesis problems. Like you started off with this molecule where you have an alcohol right next to a halogen, and then you wanted to make it the epoxide in the intermediate somewhere, and then react that with epoxide with a Grignard reagent, let's say, right? To add an extra R group.
You're saying intramolecular mixed epoxides.
This is a type of intermolecular reaction. There's many other intermolecular reactions, right? For 1,18B, 1,18C, it's just a broad reaction where the nucleophile is on the same molecule as the electrophile.
What's this mechanism called?
This mechanism is still Williamson ether synthesis, but intramolecular. So you could call this intramolecular Williamson ether synthesis.
And also, what would be a good,
Uh-huh.
like, why would we want to make epoxides?
Yeah. Okay. I'll have to explain the synthesis, like with the OR and the OH. But before I go over that, I want to go over the ether reactions, like the H2SO4 and HX waves. But I'll go back to that question. Yeah. Uh-huh. Yeah.
If you make the epoxide, the part with the Br leaving group, it should turn. If it's like R, it changes to S, and if it's S, it changes to R, or should the
yes.
It changes.
It changes. Yes. Because we're inverting stereochemistry. So if we had an R there, we're going to invert that R into an S, and vice versa, S to R. Right. Yeah. Yeah. Right. Because for intermolecular reaction, you don't have an electrophile here, right? You have to bring an electrophile as a second step, the halocane. Yeah.
If that OH was on a dash, how would the epoxide change?
If the OH was on a dash, okay, so the epoxide would change by having this weird structure here. Okay, that's a good question though, because let me erase this part right here. Yeah. Okay. It's gonna look weird, different. Yeah. If you see this OH as a dash instead, and you react that with NaH, the H minus will still deprotonate that alcohol, giving a negative charge oxygen, right? But this negative charge oxygen here is not going to attack that carbon and kick out the bromine right away, because when we invert this dash to a wedge, the epoxide is going to have a dash bond here and a wedge bond there, right? That's not stable. We don't want that, right? So what we have to do is that we're going to rotate that single bond, and I'm going to swap these two groups around, right? I'm going to make this O minus. Wait, hold on. Let's see. Go here. Let's see here. Okay, this is interesting. Okay, let's see. If I do that, I get this O minus. This dash becomes dash isopropyl. This becomes that. This becomes that. Right? Does this make sense on how I rotated the single bond and I swapped this O minus with this isopropyl, which like inverses stoichiometry? Like the O minus is now a flat bond. The isopropyl is now a dash bond, like that. I'm gonna do that one more time, but I'm gonna swap this methyl with that bromine right there. Right? And when I do that, I'm going to get a bromine here, and the dash bond is now the methyl. Right? And now this O minus is gonna attack that carbon, kick out the bromine to give us this epoxide here. Like that. Right? Yeah.
When you flip, if you wanna like flip the molecule, do you have to flip both sides? Could I not just flip the side of the BR and make it a wedge?
Oh yeah, you can make the BR a wedge, but the wedge would be on this top side, and the methyl would be on this bottom side. And if we did that, let's say, let's calculate the. Well, it's hard. Actually, let's see. So if we did that, right? Let's say we get this. O minus wedge bromine up here, dash right there. This is 1, 2, 3. So right now it looks R, right? But it's not actually R.
Oh, it's
It's S because the lowest part of the group is on the front, the wedge. So we flip it to S. This is S. Let's see if this is also S, right? Because if we flip it, then this should stay S, right? 1, 2, 3. This is counterclockwise, so this is S. So that's good. You can do that, right? So this is possible. And then when you attack that carbon right there, making this epoxide right there, when we do that, this is O, this is O. We have to invert this S into R, right? Because we're inverting stoichiometry when we attack that carbon right there, right? So let's see if this is R. 1, 2, 3. So that is, it looks R, but it's not actually R. It's S. S. Yeah. So we can't do it like that, right? Yeah. So that's how you can confirm with the R and S configuration, right? Right. But I don't think you'll get something like this on the test, but just in case it shows up. Just in case it shows up, right? Okay. Yeah. Yeah. Question?
This is going back a few steps.
Mhm.
So when you have the epoxide ring and
Yeah.
you're starting with the two dashed,
Yes.
you're rotating it so they're now both in just on like the same plane, right?
Right, like the O minus dash and the
And-
isopropyl flat bond.
Yes.
I
So,
swapped those two groups.
yes.
Right.
So now the
Uh-huh.
now on like the lower one, it's like the oxygen, the O minus is here, and the bromine is here.
Uh-huh.
They're still on the same plane for there. So how does that work?
Uh-huh.
Wouldn't they have to be opposite to work, or why does it work when you rotated them into the same plane, but not if they were in the same?
Oh right, because I would also have to invert the stoichiometry like that. They have to be in opposite planes. Right,
They
you're right. They would, right.
Okay.
Because you know how I did the other reaction, but I inverted the dash to a wedge.
Yeah.
I would also have to invert this bond as well.
Yeah. So would it have to look like this to get it backwards?
O minus agent MGBR. Oh no, this is epoxide opening.
Yeah,
This is
I know
opening
that's
up the epoxide.
opening, but going
Right.
backwards.
Going backwards. Right. That would have to be inverted.
They would.
Right.
Okay.
So let me fix that. Yeah. Yeah. Right. Okay. Yeah. So I just realized a problem here. When I attack this carbon here and kick out this leaving group, I would want to do backside attack, right? Which inverts the stereochemistry. But if we look at the line of reference right here, when we invert this bond on the opposite side of the line, that's not going to make it a stable epoxide, right? So this is not going to be the right answer. So let's see here. Yeah. So because of the stereochemistry not aligning to each other, there would be no reaction, right? No reaction of this. If the alcohol was a dash here and a dash here, the stoichiometry would not align. You'll most likely see the alcohol and the halogen as opposite stoichiometry as each other. Like if the alcohol has a wedge, the halogen would be a dash to invert the dash into a wedge like that, right? But what you can see instead is this right here. Right. So if I have this OH like that, and I have a bromine right here, even though the alcohol and the halogen here are like cis to each other, like that wedge and wedge, we can still rotate this to swap the bromine and methyl group to each other's spots, which is going to make the bromine into a dash bromine, and the methyl is going to be a flat bond like that. And then we could do the intermolecular Williamson ether synthesis like that, right? Where the NaH is going to deprotonate the alcohol, giving a negative charge on the oxygen, which is going to attack that carbon, kicking out the bromine leaving group, right? Yeah.
Could you use KH instead of NaH?
Yeah, you can use KH as well. Yeah, KH would work. Yeah. Mm-hmm.
Are you still doing epoxide?
Epoxide. Yeah, I'm still doing epoxides. Williamson ether synthesis, but we're trying to create epoxides, right? Like the H minus here is gonna grab that hydrogen, give that oxygen a negative charge, and then this oxygen here is gonna have a negative charge, which is gonna attack that carbon, kick out the bromine, and invert the stoichiometry to give us this epoxide here for Williamson ether synthesis, right? Mm-hmm. Yeah. Okay.
How exactly do you know like which bond to invert for the
Uh-huh.
epoxide?
Yeah, so think of this as an SN2-like reaction. Whenever we attack this substrate here, we are inverting the bond that gets kicked off. You could say we're kicking off this dash, so we're gonna invert that dash into a wedge bond, right? But this dash bond here has 2 electrons. Those 2 electrons are going onto the bromine to give that bromine a negative charge, like that. This new bond here that is a wedge is coming from one of the pairs of electrons on an oxygen right there. Let's say this pair of electrons is coming on the back side of the dash, which is the wedge. So when it comes on the top side, the wedge side, it creates that wedge bond right there to kick out the dash bromine.
Why is there 2 dash bonds?
Oh yeah, these are wedges.
I mean, why are there
Uh-huh.
2 wedge bonds? Sorry.
Right, because this wedge bond here stays the same. Nothing touched this carbon, so it stays the same. This dash bond here, it got attacked, so we have to invert this dash bond into a wedge bond.
But don't we dissolve that bond when we're like separating bromine?
Like we do dissolve this bond, which goes away to the bromine as this pair of electrons right here. This is the new bond here. That bond is not this bond. They're different bonds, right? This bond here has 2 electrons. Those 2 electrons are coming from these 2 electrons here of the oxygen that attacks. Yeah, this is the new bond. The 2 electrons are coming from that pair of electrons on oxygen right there when it attacks that carbon right there. Right. Uh-huh. Yeah. Uh-huh. Okay. So there's ether reactions with acids like HX, H2SO4, and that's gonna be different for different professors. So this one's gonna be a little bit iffy, right? So let me try to work this one out. Let's see, because Levin's helix does it differently, and Farhat and Wade they might do it differently. So if we have this ether here, and we react it with HX like HBr, we're gonna get like different kind of reactions, right? This is a table that I always used. Actually, I have a table for that for Lieb's class, but let me check if it correlates with your guys' class really quick. Okay. 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 This one. This 118A. Content review sessions. Okay. This is gonna be this one. 13. 14. Okay, it's gonna be 13. Right here. Okay. Oh no, that's with alcohols. Okay, got it. Right here. So this is ether reactions. Before we go over the ether reactions, let's do alcohol reactions because it's gonna relate, right? So the first reaction we're gonna learn here is nucleophilic acid reaction with alcohols. Right. So a nucleophilic acid is gonna be HX, where X can be chlorine, bromine, or iodine, right? Because when we deprotonate this HX, we're gonna get X minus. And that X minus, like Cl minus, Br minus, or I minus, is gonna be the nucleophile that attacks the electrophile, right? And you're gonna have different kind of alcohols. You can have a primary unhindered alcohol. You can have a primary hindered alcohol, secondary alcohol, or tertiary alcohol, right? And depending on what alcohol you have, you're gonna get different reactions, right? So if you guys have way, I would put this chart down on the note card, because this is gonna help you identify what reaction you need to do on the test, right? So SN2, and then everything here at the bottom is gonna be SN1, where E1 would be the minor product. But for the exam, I would definitely put the SN1 product, which is the major product, like that. Okay. Yeah. So let me give you guys some example problems to make that more clear for you guys. Let's say we have this alcohol and we react this with HBr. Okay, so before we do the reaction, what is this alcohol reacting with this nucleophilic acid going to do? SN2 or SN1? Right. SN1, right? Because we have a secondary alcohol reacting with HBr, so it's SN1. When we have a strong acid here, HBr, what is that going to do to this alcohol?
It's gonna take the H from the.
So the base would take the H from the alcohol, but this is a strong acid, right? So the alcohol here is going to take the H from the HBr, right? Because if you think about which was the acid and which was the base here, this alcohol would be the base. This is going to be the acid, right? Because in the previous example, when we did NaH with the H minus, the H minus was the base that is going to take the H from the alcohol. But this time we have a strong acid. Yep, it's protonating the alcohol, right? To give us this OH2 plus right here. And is this a good or bad leaving group? Good leaving group, right? And now let's think of this an SN1E1 type mechanism. If this is a good leaving group, what's the next step that is going to happen in SN1? Carbocation rearrangement. Wait, I mean, not yet. Carbocation formation. kick out the good leaving group, right? It's just gonna leave by itself. Once we have this good leaving group, it's gonna leave by itself, right? And when it leaves by itself, this carbon here that lost the bond is going to have a positive charge. And this positive charge on the carbon here is what we call a carbocation, right? And you have to be careful here because whenever we have a carbocation, you always have to look out for carbocation rearrangements, right? Look out for carbocation rearrangements, which can be a hydride shift or an alkyl shift. Right. So if we have this secondary carbocation here, do you guys see any positions that we could do to make this carbocation more stable? Yep, we can. On the right side, hydride shift. So I'm going to explicitly draw out that hydrogen like that. And when I shift the hydride here, that bond is going to go with it, right? Because that bond with the hydrogen is going to go make a bond to that carbocation right there. And the reason why we do that is to form a carbocation at the more substituted position, right? Because the carbocation at the more substituted position is more stable. And the reason why is because of hyperconjugation. So that might show up as like conceptual questions, multiple choice question. Hyperconjugation, the factor that makes the carbocation more stable. Now, once we have the more stable carbocation, the tertiary carbocation here, we can now bring in our nucleophile, Br minus, to attack that carbocation, giving us our final product here, like that. Yeah, there's no more because this carbon here is sp2, which is flat and planar, right? And if it's flat and planar, there's no stereochemistry. So this Br minus here can attack on the top side or bottom side. It doesn't matter. You could say, no, this is not racemic because we don't form enantiomers here. But if this was a propyl group, then you can say racemic. Yeah. Uh-huh. Yeah. Okay. Have you guys learned about concerted hydride shifts or concerted methyl shifts? No? Okay. So I would not worry about this case, the primary hindered case, because this primary hindered case does a concerted shift, right? That's more for Liebman's class, but I think you guys would have to worry about primary, secondary, tertiary. Let's do two more and move on to the next one here. Right. Okay. Yeah. Okay. Okay. So if we have this ring and we have this alcohol with HBr, what would you get? Try that one and this one here. Let's do HCl. Keep using HBr. HCl.
primary unhindered, does that mean the whole molecule is unhindered, or it's just the alpha or beta carbon is unhindered?
Yeah, the alpha carbon that is the beta carbon,
Beta carbon's unhindered.
unhindered, right? So if the beta carbon has more than more than one substituent, then it's hindered. Wait, I'll show you an example of that right here. Right. Yeah. Yeah. Right. So primary unhindered would be like this OH, where this is the alpha carbon, this is the beta carbon. Primary hindered would be like this is the alpha carbon, this is the beta carbon. And if this beta carbon here has more than one substituent, then this is hindered. Right? Making this a primary because it's still a primary alcohol, but it's hindered because the beta carbon is hindered. Yeah. Yeah. Okay, I'll show you that just in case it shows up. So if you had a hindered alcohol like this, and you react this with HBr, the first step is still the same. We protonate the alcohol to create the oxonium ion, good leaving group. Right? But the next step here, we want to kick out that leaving group, right? Which forms a carbocation on this carbon, which is a primary carbocation. That's not stable. We don't want that. So we cannot kick that leaving group off right away because it would form an unstable carbocation. So what we have to do is a concerted hydride shift, where if you see a carbocation here, you would want to do a hydride shift to make the carbocation into a more stable tertiary position, right? So we're going to do it at the same time. This hydrogen right here is going to shift over there, kicking out the leaving group at the same time, which is why it's concerted simultaneously, right? When that happens, we get this carbocation here, and then the Br minus can just attack that to get the final product. Yeah, but I don't know if this will show up on your guys' exams, like if you guys haven't gone over it, but this is what it would be if you had a primary hindered alcohol. Right. Yeah.
I guess some
Yeah.
for the one with HCl,
Uh-huh.
like because it's SN2, it wouldn't shift over to the more.
Mm-hmm.
And for the it like because it at least ways it says like primary cations don't exist.
They don't exist.
So
Yes.
that's just for like primary hindered where it's like a special.
Yeah, so primary hindered would still avoid that primary carbocation being formed because once we have the good leaving group here, we are not forming this primary carbocation. We're going to this tertiary carbocation right away because we're doing the hydrogen shift and the leaving group at the same time, right? If this was a secondary carbon, then that hydrogen shift would not happen with it. Right? It would just leave to form that secondary carbocation, and then we do the hydride shift, right? So that way, thing that primary carbocations cannot exist is still applying here. It cannot exist. Yeah. Yeah. Yeah.
If this leaves, wouldn't that be also primary?
That would also be a primary carbocation, right? But before you do this reaction, look at what reaction it would do. What kind of alcohol is this here? Primary unhindered with HCl, SN2. So the leaving group would not leave by itself for SN2, right? You guys have any questions here? No, it's good. Okay. You guys got it. That's good. Yeah. Okay. Yeah. Okay. So the first step of the mechanism here. Yeah, no problem. Is going to protonate the alcohol to become this good leaving group here. Okay. Now, what's the next step here after we protonated it to make it into a good leaving group? It leaves, right, to form carbocation, right? And then once we have this carbocation, shifts to tertiary position, doing that hydride shift. And then once we have that, at the Br, Br minus comes in, attacks that carbocation to give us that final product right there, right? And this was a secondary alcohol, making this SN1 type mechanism, right? But what kind of reaction would this? Yeah, yeah. Oh, why wouldn't that be wedge? Because when we have this carbocation right here, this is sp2 hybridized, and the geometry of that is flat and planar because it's trigonal planar. And because it's flat planar, the Br minus can attack on the top side, giving us a wedge product, or the bottom side, giving us a dash product. Right, so this could be a wedge or a dash. Yeah, so it's gonna be, it's not gonna be racemic because this is not a chiral center. If we had this right here, then we could say racemic, right? Yeah, yeah. Because racemic is a 1-to-1 mixture of enantiomers, right? 1-to-1 ratio of enantiomers. But we can't have any enantiomers here because that's not a chiral center. This group is the same as that group right there, right? Okay, so what kind of reaction would this be here if we have a SN2, right? So what would be the first step between the HCl and this primary alcohol? Protonate to create this oxonium ion good leaving group. Now, what would be the next step if this was SN2? Backside attack. Yeah, the leaving group here does not leave by itself, right? Because we cannot form that primary carbocation. And this is not primary hindered, so we cannot do this concerted shift, right? Because the beta carbon here is not substituted, right? So the Cl minus here is going to attack that carbon, kick out the leaving group to create this final product here, like that, right there. Right. Yeah.
So what's the difference between using HBr versus PBr3?
HBr, oh yeah, that's a good question. HBr will have the carbocation intermediate, right? If we do SN1, which has a chance of doing carbocation rearrangement, which would put the Br at a different location where the Br was originally. But PBr3 is straight SN2. It's always SN2. PBr3, SOCO2, and PI like 5 or something like that, which would invert the circumvention of the alcohol at the same exact spot. No shift, no carbocation rearrangement at all, right? Yeah. Uh-huh. Yeah. 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 Uh-huh.
Just like on that note,
Yes.
because that does make sense, but we did go over the note for like PX3,
Mhm.
so like PBr3 or SOCl2.
Mm-hmm.
It does SN2, but on a tertiary it would do SN1. I guess like there is a carbocation, but it wouldn't shift, so it doesn't really matter. Right?
Yeah.
Okay.
Yeah. Thank you for showing me this. I didn't know that. Yeah. But it would be SN2 for primary and secondary.
Okay,
Yeah.
got you.
Yeah. Mhm. Yeah.
I don't know if you have enough time, but
Uh-huh.
because I heard we're gonna have epoxides with synthesis.
Epoxides with synthesis. Yeah.
And I heard that's like the hardest.
Hardest one. Okay. Yeah. I'll end up the session with the epoxide synthesis. But before that, let me show you guys the other tables of this first, right? And then I'll send you guys like this practice problems with like these tables after. Yeah. With my notes as well. Let's see here. Okay. I'll email it to you guys here after the session. Yeah. Yeah, like, you just type your emails in the Google Drive. Yeah. Uh-huh.
So
Yeah.
for the PR, it attacks from the front side. Is there a reason why? Or can I
Yeah.
attack from the back?
It could attack on the back side as well.
Okay.
Like 50-50, front or back, doesn't matter. Yeah.
Okay, cool.
Right. Uh-huh. Yeah. Okay. So the other table that you guys should know is the non-nucleophilic acid reactions with alcohols, right? And non-nucleophilic acids are going to be sulfuric acid, H2SO4, and H3PO4, right? And this is going to be based on temperature, because the alcohol is going to be the same. Primary, unhindered. Primary, hindered. Secondary, tertiary. And the reaction that you have can be different. For leavens, it was like 135 degrees Celsius and 180 degrees Celsius. That would change up the reaction, right? SN2, E2, SN1, E1. Right. Yeah. Because high temperature, like high heat, would favor the elimination reaction to create the double bond. Right. But lower temperature would prefer the substitution reaction, SN2, SN1. Okay. Okay. Yeah. Okay. So the last type of reaction that I want you guys to know for alcohols, wait, there's more reactions like redox, but then for this one is SN2 like reactions with alcohols. So let's say we have this alcohol here that is dash, and you react it with these three weird reagents here. SlCO2 or PCl5, PBr3, or let's add this group right there as well. Yeah, PI2. This is going to do SN2 with the halogen that the reagent has. SlCO2 and PCl5 has chlorine, so we're going to invert the alcohol with chlorine like this. So that dash is going to be into a wedge chlorine. For PBr3, it's going to be bromine. For PI2, it's going to be iodine. Right. And it works for primary, secondary, and tertiary alcohols. Right. It works with all alcohols, primary, secondary, and tertiary. Yeah.
Going back to the non-nucleophilic acid.
Yeah.
What's the mechanism
Uh-huh.
that because H2SO4, how does that react with the alcohol?
Yes. For let's say we have H2SO4 and 180 degrees Celsius for E1. If we have, okay, let me do it down here. Right. Okay. Yeah. Let's do it down here. Yeah. Okay. So if we have this alcohol and we react it with H2SO4, 180 degrees Celsius. This is a secondary alcohol. We have 180 degrees Celsius with a non-nucleophilic acid. So that's going to be E1. Right. What do you think the first step is going to be in this mechanism when we have a strong acid and alcohol? Yeah, protonate the alcohol to turn that into a good leaving group. OH2 plus. And if it's an E1 type of mechanism, what's the next step after we have the good leaving group? Leaves forming a carbocation intermediate. Now, what would be the next step after we have this carbocation intermediate? Hydride shift, right? To create the more stable tertiary carbocation right here. Now, once we have that carbocation, if we are going to do E1 because we are in high temperature, right? Usually SN1 is major over E1, but if we have high temperature, E1 would be major, right? If we have high temperature, then what would be happening next once we have this carbocation for E1? Yeah, it could be this hydrogen, or this hydrogen. We want to make the more stable alkene, so we grab the most substituted hydrogen, which can either be this hydrogen or this hydrogen here. And instead of water, we're going to use the HSO4 minus that got kicked out earlier, the conjugate base. Right, grab that hydrogen, make a double bond there to create the alkene, like that, right? E1. Yeah.
Does it have to be or like
Uh-huh.
it'd be wrong to put like water takes it.
If you don't have water in the reagent, then it would be wrong. But if you do see water in the reagent, or you created water somewhere in the mechanism, like you picked up water, then you could use water
Okay.
in the.
You don't assume that because like H2SO4
Mhm.
like is.
Oh yeah, it is. Yeah, it is in water. So you could use water as well, and I don't think your professor would take points off for that. Yeah. Yeah.
So if it's SN1 or SN2,
Uh-huh.
what's gonna do the backside attack, or what's
Oh,
gonna do the
yeah. That's a good question. The alcohol itself. So let me show you an example of that. Yeah. Okay. Any questions on this mechanism, on how I got the E1 type mechanism here? Yeah. Yeah.
So
Uh-huh.
the table that you wrote,
Yeah.
you said SN2
Mhm.
will react tertiary to make haloalkanes. That
Oh,
doesn't
SN1
happen.
always.
It's SN1, right?
Yeah, it's SN1, right?
Okay.
For alcohol to haloalkane with these reagents here.
Okay.
SOCO2, PCO5, P3, PI2. Right.
So that would be primary and secondary SN2.
Yeah, primary, secondary, SN2. Right. Right. Yeah.
Okay.
Mhm.
I just wanted to confirm.
Yeah, you're comparing different tables that you're seeing different
Yeah.
areas. Yeah, it would. And for tertiary, these ones here would do SN1.
Okay.
Right.
All
Mhm.
right. Thank you.
Yeah, no problem. Okay. Yeah. After we do the hydride shift,
If for E2, it's
this carbon here gained a bond, which is this hydrogen here,
And then you put
positive charge there. Yeah, carbocation here. Once we have this, we do E1. So this is the carbocation here. We could take this hydrogen, or this hydrogen, right? The one away from the carbocations to make a double bond here, or here.
so you should take this one.
Yeah.
or
Right. Okay. So let's do the example with primary alcohol. Okay. So if we have this alcohol here reacting with H2SO4 in 135 degrees Celsius, we have a primary unhindered alcohol. We have low temperature, so this is SN2 reaction, right? But for all SN2, SN1, E1, E2 reactions, we require a good leaving group. This is a bad leaving group, so the job of the acid is to convert this OH into OH2 plus good leaving group, protonate it, give it a positive charge, which makes it into a good leaving group. Right? Now, if this is SN2, assume excess of this, right? Excess amount of this alcohol floating around. This second equivalent of the alcohol here is going to make an ether by attacking that carbon and then kicking out that leaving group here, which would create the ether, the symmetric ether. This is the dot carbon. This is the new bond between that dot carbon and oxygen. And this oxygen here is attached to CH2 benzene and a hydrogen with a positive charge. Now the last step here is to neutralize this positive charge oxygen with water or HSO4 minus. Grab that hydrogen, give that oxygen a pair of electrons, which makes it neutral. And this would be a symmetric ether, like that. Right. Ether, West, we went over that. Okay. Okay, there's two more tables here. Okay.
just like trying to visualize how that
I had a question.
Yes.
So for non-nucleophilic acid,
Uh-huh.
it says heat. Then
Mhm.
would it be good to assume it's either E1 or E2? Because sometimes, like when you see heat, it can be SN1 and SN2.
When you see heat, it could be SN1 or SN2. Like just like heat or
Just
delta symbol,
heat, like no temperature.
no temperature. Um, and if you had like any type of alcohol and you just see heat with it, like primary unhindered, primary hindered, secondary, tertiary. In general, if you so that would depend on your professor. Like I would ask your professor about it because usually like Levens, she's very clear and straight with it. She assigns the temperature, but you have Wei, right? Like Wei, if she follows with Levens problem sets, then you would see this right here. But if in general, if you see heat, I would lean towards the E1, E2, right? Because heat would increase the temperature, leading towards the elimination reactions, right? Yeah.
Could you show the E2 mechanism?
E2 mechanism, yeah. E2 mechanism, let's do that here, which is going to be primary unhindered 180 degrees Celsius. Yeah. Okay. Right. So if we have this alcohol reacting with H2SO4 180 degrees Celsius, same step, protonate alcohol, make it into a good leaving group. Once you have a good leaving group, we know that this cannot be SN1 or E1 because when we kick off this good leaving group here, we form a primary carbocation, which is unstable. It cannot exist. So that's why it's going to be E2 if we have 180 degrees Celsius, or SN2 if we have 135 degrees Celsius. So the base here is going to be this excess amount of alcohol we have, which is going to, let's say, we draw another one here. Well, actually, the base that we could use here is, we could use the alcohol or the conjugate base that we made earlier to grab that hydrogen, make a double bond here, kick out the leaving group to form alkene there. Right. So the base here could be your HSO4 minus that you kicked out in the first step, or another alcohol, a second equivalent of the alcohol here, second equivalent, or water, right? To grab that beta hydrogen, make a double bond, kick out the good leaving group to form the alkene there. Yeah. Yeah. Right. Okay. Okay. Now let me give you guys two more tables here for ether reactions. Yeah. Okay. Let's get ether reactions. Yeah. Oh, protecting groups. Yeah. Yeah. Let's go over. Let's see if I, because let's see. Yeah. I probably can go over that, but we'll see. We'll see if we have time or not for that. Yeah. Let's see. Let's see. Nucleophilic acid reactions with ethers. So the R group attached to the ether, it could be methyl, primary unhindered, primary hindered, secondary, or tertiary. And the reaction that you're gonna have is gonna be either SN2 or SN1, right? Where the E1 is minor, SN1 major, right? So we're gonna have that, this, that, that, yeah, that right there, right? So that's the reaction with nucleophilic acid reactions with ethers. And the selectivity here is very important, right? Because if you have an ether with two different R groups, you're gonna select for one R group over the other, right? Tertiary is gonna be higher than methyl, which is higher than primary unhindered. which is higher than primary hindered. And the lowest one is going to be secondary carbon. Right, so let's look at some examples to make this more sense. Make more sense. Okay, so if we have this ether here, and let me give you another one. Let's say this ether here. Okay, the first thing that you would do is identify what the R groups are attached to this oxygen ether. This is a tertiary carbon because it's attached to 3 other carbons. This is a primary carbon because it's attached to 1 other carbon, right there. Right, now if we look at the selectivity ranking list, tertiary is prioritized over primary unhindered carbon, right? So we're gonna focus on this tertiary row right here of the table, which is gonna be an SN1 reaction, right? Now, let me ask you guys this. What do you guys think the mechanism is gonna be like if we have this ether and strong acid HCl? What will this strong acid protonate here? Yeah, the oxygen is gonna get protonated by the HCl, giving that oxygen a hydrogen. And what charge as it gains that hydrogen? Positive charge. Now this is the good leaving group, right? And this is why we had to choose one carbon over the other, because this could be our good leaving group here, or this could be our good leaving group here, right? But we chose the tertiary carbon to be the priority. So we're gonna do SN1 where this is gonna be the leaving group right there, right? Making this the good leaving group, right? Because this tertiary carbon wins over the primary unhindered carbon. That's why we're prioritizing that tertiary carbon, making this the good leaving group. Right? And when we do that, we're gonna form this carbocation and this alcohol here, that left. And the final step here is that the Cl minus is gonna attack that carbocation to form this product plus the alcohol that left earlier, like that. Right. Okay. So before you identify the types of R groups, I would protonate the alcohol, not the alcohol, the ether first, the oxygen ether first, right? So the first step, protonate the oxygen to give that oxygen a positive charge. Like that, okay? Now once we have that protonated leaving group, what would take priority? This tertiary carbon or this primary unhindered carbon? Tertiary, right? So if this tertiary carbon is the priority, this would be the good leaving group. Right, we're gonna kick off that leaving group off like this, which is gonna form the carbocation here, where I minus is gonna attack that carbocation, giving us this product plus the alcohol that left as a leaving group. Okay, so the first thing you would do, protonate the ether oxygen to get the leaving group. Then you choose which carbon of the ether will take priority based on the selectivity ranking list. And then you look at this table to see what reaction it would do to do that reaction for ethers. Yeah.
Why is the whole part encircled lead and not just the OH?
Oh, like this OH right here? Not this OH? Yeah, this whole OH here, this oxygen is also attached to this R group right there. So when the OH leaves, this, because we're only breaking one bond here, we're breaking this bond to go to that oxygen, so the OH will leave, but this O here is also attached to this alpha group there. Oh, what makes this bond leave? So if you think of this as SN1 reaction, right? like if I show you this right here, like the same group with the O, that positive charge here, we have two possible leaving groups. The leaving group that I showed you earlier, this one here, that's one possible leaving group. The other possible leaving group would be this right here. This whole thing, right? And that makes us have two different possible electrophiles. If the blue was our good leaving group, this would be our like substrate carbon. If the red was our leaving group, then this would be our substrate carbon right there. Right? Because if this was like an SN1 reaction, let's say SN2 reaction, if the nucleophile comes in to attack this carbon, and we kick off this bond to the OH right here, the OH with this whole bulky R group leaves with it. Right? But I didn't choose the red as my leaving group because when we did the priority list, tertiary is prioritized over the primary unhindered carbon. So that's why this is our leaving group right here, not this red carbon group right there. Yeah. Yes, right. And we want to do SN1 over SN2, right? Based on the selectivity ranking list and the table reaction right there. Right. Yeah.
Would HCl and HBr and HI versus HF be different because fluorine is less selective?
Yeah. So we don't usually do this with fluorine because F minus is very like unstable, unreactive. But if you use HCl, HI, HBr, it wouldn't affect the reaction. Yeah. Yeah. Okay. Okay. There's one more table here, and then we'll be finished. Which is the reaction with non-nucleophilic acid with ethers. Right. Yeah. Okay. And I'll show you guys my 118A content review drive when I did the content review sessions for ATC in winter 2024 for you guys to review these notes and practice as well. Let's see. Okay. Non-nucleophilic acid reactions with ether. Non-nucleophilic reactions with ethers. So these non-nucleophilic acid are H2SO4 or H3PO4. Right? Same kind of R groups. You can have methyl, primary unhindered, primary hindered, secondary, or tertiary. Right? Oh, what the heck? Is this the same reaction? Yeah. And then you can see heat as well. Reaction. Wait, what the heck? Yeah. Oh, it is the same reaction. Same table. Oh, same table then. Dang. Okay. So SN2, SN1, minor. So the same table as the last one. Right. Okay. So let's give some examples here. Let's say we have this ether reacting with H2SO4 and heat, or we have let's say this ether here. This ether here reacting with H2SO4 and heat. So the first thing that you would do is protonate the ether oxygen to make that into a good leaving group. Right. Now, once that's a good leaving group, then you find the R groups attached to this oxygen here, which is this R group and that R group there. Which one would take priority? based on the list. And the list is the same as well, which is tertiary over methyl over primary unhindered over primary hindered over secondary, right? For the selectivity, right? So tertiary versus primary unhindered. Tertiary is higher in the list than primary unhindered. So we're gonna have this tertiary carbon be the substrate, the electrophile. And if that tertiary carbon is the electrophile, then this is our good leaving group here, right? And if this is the tertiary carbon here, we're gonna do SN1, right? Where this leaving group here is gonna leave, form a carbocation here. This is the side product that left, alcohol. This is an excess, right? So the nucleophile here is this ether here. Wait, what? SN1. Well, how would that get deprotonated? Is this with? Do you guys have Levin's ether reactions practice worksheet? Yeah, I made it.
Where it's like OH is on both ends.
OH is on both ends.
I just don't really know how
Yeah.
they get an OH.
Wait, can I see? Can I see on your
Oh yeah.
iPad? Yeah. Because the way I did this was like I said from Levin's ether reactions practice, problems B, F, N, T, X, Z, and AF. But I don't have it with me right now. Yeah.
I'm trying to find the one where it has like.
Ether. Oh, these are the ones with
oh.
alcohols. Right.
Right,
Uh-huh.
okay.
Mhm.
Yeah, this one. This one is like a ring.
Mhm.
Ether, and then
H2SO4 and heat. Oh, and it breaks it open with water.
and
Water.
then it ends up with OH,
OH on both
that are
ends.
broken.
On both ends, secondary, primary unhindered, water. Oh, okay. So this right here, you'll see with water. H2O, that's important. Right, so let's put water here. H2O. Right. Okay, so if water is there, the nucleophile here is this water, right? Not this ether here. Because I was like, if this ether attacks, then we can't deprotonate that oxygen. That doesn't make sense. It makes more sense if water is a nucleophile, right? So water here is going to attack this carbocation to give us this intermediate here, right? Where this is the new bond between the carbon and oxygen that attacked that carbon right there. And this oxygen here that attacked that carbon is attached to two hydrogens, which are these two hydrogens here, 1, 2. And because it has 3 bonds, it's positively charged, 1, 2, 3. And the last step here is just to deprotonate it to make it neutral alcohol, like that. So that's one of the products, and this is the other product here. So we get 2 alcohols as a product. This tertiary alcohol and this primary alcohol here. Right. So this right here is very important. The key nucleophile, water is there. And that's the water that attacks the carbocation, not this ether. Right, not that ether. Okay, let's put water here as well. Yeah. Do you want to try this mechanism here? Like protonating it and attacking it, or doing the reaction? Here, you can try. And then you can walk yourself through it, and then I could check. It's okay if you make mistakes. It's okay, yeah. Other people might have the same problems as well. And you can learn
So
from
it's
it.
like the same thing, right? So
Yeah.
SO4.
Yeah.
It's gonna protonate.
Right. Other way, right. The oxygen grabs the H, and then that bond kicks off the HSO4 minus, like that, right? Right. Okay. And positive charge.
And then it breaks off somehow.
Right. So we have this secondary carbon and primary unhindered carbon. So let's label that like this. Yeah, secondary and primary hindered, you could say.
So this is right.
Yeah, primary. And based on the selectivity factor, what is higher? Second. So on the list, secondary is the least. Primary, right? So if the primary is the electrophile, we could dot that, and making this the leaving group,
Right.
right? Because if this is prioritized, then that would be the electrophile, making this the leaving group, right? So this would be the leaving group here, and this would be the electrophile.
Does it just leave because it's SN1 first?
Yeah, it would leave because it's SN. Oh wait, actually, in this case here, this is a little bit more difficult. I didn't realize that because when it leaves, what kind of carbocation is going to get formed here?
It's a primary carbocation.
Yeah, and it's not stable to exist by itself.
Right.
It cannot stable, right? And can we do a concerted hydride shifter? Are there any hydrogens on this carbon?
No.
No carbons, so we can't do SN1 here.
So you have to do SN2?
SN2 like reaction. And we're going to use water as a nucleophile here. So draw out some water floating around somewhere, right? And then the oxygen of the water is going to attack that electrophile and kick out the leaving group. Right. Yeah. Right. Only two pairs.
Oh,
Two
right.
pairs. Right. Right. And
It's
then
gonna kick out this water?
yeah, kick out this alcohol. Right. Kick out the bond onto the oxygen. Yeah, that's right. That's right.
Oh, that's
Right. And now let's draw out the intermediate here.
Oh.
Right. That's the leaving group that left, alcohol, right?
Oh.
And then this carbon here is now attached to
The H2O.
the oxygen H and positive charge on that oxygen. And the last step is to just
It gets deprotonated by H2O.
yeah, H2O or HSO4 minus. Yeah.
There's no space.
Yeah, no space. Right, we can draw it up here. Grab the H. Yep. Bond between the H and oxygen goes there. Yep. Nice. And that would just give us this final product here.
Just HO and the.
Oh yeah.
The benzene. Right?
HO and the benzene right here. Yeah.
Okay.
And this is the other side product here. Right. So the first thing you do, protonate the ether oxygen to get the good leaving group. Once you get the good leaving group, then you find the two R groups to see what takes priority, right? And then once you find the priority group, then that's gonna be the electrophile carbon, right? Tertiary is higher than primary unhindered, making this the leaving group. And then you look at what reaction we do. Tertiary SN1, so this is gonna leave from a carbocation and do the whole reaction like that, right? Yeah. Any questions on this table? Yeah. Yeah. Okay. Yeah. Okay, so the review session is gonna end here, but I'm gonna send you guys the 118A review documents. But do you guys want to take a quick picture? Quick selfie picture? Let's do it. Let's do it. Yeah. Okay, let's take a 0.5.
Oh yeah.
0.5. Yeah. Picture. Yeah. Yeah. Yes. I want to get all the tables here. Yeah. Yeah. Okay. Okay. 1, 2, 3. 1, 2, 3. 1, 2, 3. Okay. Yeah. Thank you.
I had a quick question.
Yeah.
You know how you were mentioning about writing your emails in?
Right. Yeah. It's right here. Here. Let me share you guys this right here. 118A content review, leave-ins, share. Yeah. Okay. Just put your email there. Yeah.
Wanna go ahead? Okay.